Hello everyone, in this video we are going to discuss about flip-flop. A circuit that has two stable states is generally treated as a flip-flop. These two stable states are used to store binary data. There are two stable states and these two stable states are used to store binary data. Generally flip-flop is nothing but a 1-bit storage element. In the sequential logic circuit, the flip-flop is the basic storage element. There are two basic storage elements, one is flip-flop and another one is latches. This flip-flop could be constructed using 4 NAND gates and 4 NOR gates. Using 4 NAND or using 4 NOR gates, we could construct any basic flip-flop. There are 4 types of basic flip-flops. They are SR flip-flop, JK flip-flop, D flip-flop and T flip-flop. The first one is the SR flip-flop. We have seen that there are two basic storage elements. One is latches and another one is flip-flop. And there are two triggering systems, edge triggered or level triggered. Usually the flip-flop is edge triggered and the latches are level triggered. Flip-flop is edge triggered whereas the latches are level triggered. If the output value changes on the positive edge of the clock, then it is called positive edge triggered flip-flop. If the output value changes on the positive edge of the clock, then it is called positive edge triggered flip-flop. If the value changes on the negative edge of the clock, then it is called negative edge triggered flip-flop. Usually the clock pulse will be denoted by this. This is the positive edge. When it rises from 0 to the maximum value, it is called positive edge, and when it falls from the maximum value to 0, it is called as negative edge. When the output value changes at this point, this is called as positive edge triggered flip-flop. If the value changes at this point, then it is called negative edge triggered flip-flop. We have seen that there are two stable states. One is Qn plus 1, which is the present state, and another one is Qn, which is the previous state. Qn plus 1 is the present state and Qn is the previous state. For SR flip-flop, there are two input. One is S and another one is R. Using 4 NAND gates, we have designed this SR flip-flop. S stands for set and R stands for reset. This is the truth table of SR flip-flop. When S and R are equal to 0, the present state will be equal to the previous state. The present state will be equal to the previous state when both the values of S and R are equal to 0. Then the reset value is set to 1. When the reset value is equal to 1, irrespective of the previous state, the present state Qn plus 1 will be equal to 0. The present state Qn plus 1 will be equal to 0 when the reset value is equal to 1. When the set value is equal to 1, irrespective of the previous state, the present state will be equal to 1. Irrespective of the previous state, the present state will be equal to 1 when the set value is equal to 1. When both the S and R values are equal to 1, the output will be undefined. The output could not be defined when both the values of S and R are equal to 0. To overcome this, we have designed one more flip-flop called JK flip-flop. The JK flip-flop is used to remove the drawback of the SR flip-flop. That is the undefined state when both the values of S and R are equal to 1. This JK flip-flop is formed by doing some modifications in the SR flip-flop. This is just the same diagram as like SR flip-flop, but one small change is the output is fed back as an input to the first stage of the NAND gate. The output Q bar is fed as an input to the first stage NAND gate. Similarly, the output Q is also fed as the input to the first stage NAND gate. This is the drawback of the SR flip-flop. When S and R input is set to true, that is 1, the SR flip-flop gives an inaccurate result. The output of the SR flip-flop will be inaccurate. To overcome this, we have designed this JK flip-flop. This is the truth table of JK flip-flop. This is similar to S. J is similar to S and K is similar to R. Okay, when both the values of J and K are equal to 0, the output present state Qn plus 1 will be equal to Qn. Then when both the values of J and K are equal to 0, when the value of K is equal to 1, irrespective of the previous state, the present state will be equal to 0. When the value of K is equal to 1, the present state will be equal to 0 irrespective of the previous state. When the value of j is equal to 1, irrespective of the previous state, the present state will be equal to 1. When j is equal to 1, the value of present state will be equal to 1 irrespective of the previous state. When both the values of j and k is equal to 1, this is the case that causes inaccurate result in SR flip-flop. But in case of JK flip-flop, when both the values of j and k are equal to 1, the output will be the inversion of the previous state. The present state will be equal to the inversion of the previous state. If the previous state is equal to 0, then the present state will be 1. If the previous state is equal to 1, the present state will be equal to 0. This is the JK flip-flop. Next, the D flip-flop. D flip-flop is also called as data flip-flop. This could be generally used as a buffer. The D flip-flop is widely used in digital system. For example, it could be used in shift registers, counters, and input synchronization. In case of input synchronization, this is nothing but the value applied to the D input will come across the output, that is the present state q of t plus 1. When the D input is 0, the output qt plus 1 will be equal to 0 irrespective of the previous state. In D flip-flop, the previous state will not have that much role to play. The applied input will appear across the present state output. The applied input will appear across the present state output. If the applied input D equal to 0, the output will be 0. If the applied input D equal to 1, the output qt plus 1 will be equal to 1. This circuit is similar to the SR flip-flop. In SR flip-flop, we have two input, S and R. So we applied S for the one NAND gate and R for another NAND gate. But in case of D flip-flop, we have only one input, that is D. So we are applying D as an input to the first NAND gate and D bar as an input to the second NAND gate. D bar as an input to the second NAND gate. To obtain D bar, we are connected an inverter over here. And second stage is similar to the SR flip-flop. There is no change in the second stage. Next is the T flip-flop, which is also called as toggle flip-flop. D flip-flop is called as data flip-flop and T flip-flop is called as toggle flip-flop. Just like JK flip-flop, T flip-flop is also used. D flip-flop is similar to SR flip-flop. D is similar to SR, where T is similar to JK. D is similar to SR, where JK is similar to T. Unlike JK flip-flop and T flip-flop, there is only single input with the clock input. In JK, we have two input, J and K, whereas in case of T flip-flop, we have only one input, which is nothing but T. This is the truth table of toggle flip-flop. It has one input T. When the input value of T is 0, the present output is equal to the previous output. Present state is equal to the previous state. When the T value is 1, the present state is equal to the toggled version of the previous state, and the present state is equal to the toggled version of the previous state. And the previous state is 0, the value of present state will be equal to 1. So the previous state is equal to 1, the present state will be equal to 0. When T equal to 1, the output is equal to the toggled version of the previous state. The second stage is just similar to the JK flip-flop, and for the first stage there are two NAND gates. In case of JK flip-flop, we have two inputs J and K, and so we have applied one input for J and one input J for one NAND gate and another input K for another NAND gate. In case of T flip-flop, we are having only one input, and so we have applied this one input T as input for both the NAND gate. Both the NAND gate receive T as its input. Clock is applied to both the NAND gate because all the flip-flops are edge triggered. Now we are going to convert D flip-flop to T flip-flop. This is the truth table of T flip-flop. When the T flip-flop input T equal to 0, the present state will be equal to the previous state. The present state will be equal to the previous state. This is the present state. and this is the previous state. This is the previous state. Present state will be equal to the previous state. When the toggle flip-flop T input is 1, the present state will be equal to the complement of the previous state. When the previous state is 0, the present state will be equal to 1, and the previous state is equal to 1, the present state will be equal to 0. This is the excitation table of T flip-flop. Now this the first 3 columns just represents the excitation table of T flip-flop, and we have to see for what value of D we could get this output value Q of T and Q of T plus 1. For what value of input D we get this Q of T and Q of T plus 1. For the output to be 0, the input for the D flip-flop is 0. We have seen that the D flip-flop is nothing but just like a buffer. The applied input will appear across the output. So the input that we require is nothing but the output that we obtain. So D will be equal to Qt plus 1. When Q of T plus 1 equal to 0, the input D equal to 0. When it is 1, the input D equal to 1. Now we are going to derive an equation for D using Qt and Q of T. Using T and Q of T, we are going to derive an equation for D. If you see this truth, if you just compare T, Q of T and D, we could see that this T and Q of T are input. Assume that Q and T and Q of T are input and D is output. D is the output and T and Q of T are input. When both the inputs are same, either 0, 0 or 1, 1, the output is 0. When both the inputs are different, the output is 1. This is similar to the XOR operation. So D is nothing but the XOR of T and Q of T. The D is nothing but XOR of T and Q of T. This is the symbol for XOR operation. The XOR of T and Q of T is nothing but D. Now we are going to apply this equation to the input of D flip-flop. We are going to convert D flip-flop to T flip-flop. So the base flip-flop is the D flip-flop, and in the place of D input we are going to apply D equal to T XOR Q of T. To get to XOR T and Q of T, we are using XOR gate, and for this XOR gate T is applied as one input and Q of T is applied as another input. And now the output of this D flip-flop, and now the output of D flip-flop will be similar to the T flip-flop. Thus we have converted this D flip-flop to T flip-flop. Meanwhile, we could convert any flip-flop to any other flip-flop. T flip-flop to D or JK to SR. We could convert any of the basic flip-flop to any other basic flip-flops. Thank you.